Algebraic Reasoning, Chapter 1.5, Exercise 17 through 24. In the previous video lesson, we went over a scenario using data to determine an exponential function, in that case for the value of a car using depreciation. This is a similar type of problem. There are two major sets in this set of exercises. There's 17 through 20 and there's 21 through 24. I'm going to go ahead and do 17 through 20, and it's going to be quite similar to, again, the prior video. And so for question 17 through 20, use the following situation. The biologist is recording the population of a certain bacteria in a petri dish. He determines the number of bacteria in the dish every 2 hours as shown in the table below. And here you have a table. You have 2-hour intervals. And question problem 17, does the data show exponential growth or decay? Explain. Well, I'm going to go ahead and say exponential growth. And why an explanation for that? Because numbers of bacteria are increasing. And we'll just verify that briefly. And so we see increasing. We're going from 8 to 12, from 12 to 17, from 17 to 24, from 24 to 34, and from 34 to 50. And so really it looks like we're going up every 2-hour intervals, it says, right? 0 to 1, that's a 2-hour interval. So that 0 to 1 is a 2-hour interval. And total number of hours here in the second column. So our ratios, and this is what we call growth by cell division. So this is a common use of an exponential function. So what are those ratios of growth? Well, we have 12 divided by 8, and I already know what that is. That's going to be 1.5. Then we have 17 divided by 12. Let's see what that is. Next we have 24 divided by 17 equals that. We have 34 divided by 24. And finally we have 50 divided by 34. So we're going to go doing this. Okay. Next. You get a new page. We have 17 divided by 12. Okay, and we're going to decimalize that. Okay, looks like 1.42 roughly. Next we're going to have is 24 divided by 17. And then we decimalize that. We get, again, 1.41. That's pretty good. Pretty consistent is what I mean. Then we have 34 divided by 24. And decimalize, that's going to be, again, 1.416. And the last we're going to have is 50 divided by 34. And and that's going to be decimalized into 1.47. So we're going like, I mean, we start out at 1.5, 1.42, 1.41, 1.41. So if we use a mode, right, we're going to get about 1.42. So you can do it different ways. Okay, you can say, okay, we have 1.5. We'll be consistent with the others. 1.5, 1.41 plus 1.42 plus 1.42 plus 1.47, and we'll just take an average of these, and then we divide by 5 to get that. So we get 1.44, we'll say. So we're going to go with our common ratio of 1.44. So R equals common ratio equals 1.44. So that's going to be our exponential model. So we have the f of x and x. So f of x, okay, is going to be equal to our initial value, our initial amount, which is 8 bacteria, times our common ratio, 1.44, to the power of x. And then that x is going to be every 2 hours. So this will be our equation here. That's our exponential model. And we have our model. Let's go to question 19. Use your exponential model to determine approximately how many bacteria will be in the petri dish after 1 day. I'm going to write this model here. We have a new page. We'll say f of x equals 8 times 1.44 to the power of x. So I have that model right here for view. And after 1 day, let's go look at that table. Now, you have 2-hour intervals. Now, 1 day is 24 hours, right? And so we go up here by a number of hours, 0, 2, 4. Now, to get 24 hours, that would correspond with the x value of 12. So let's go here. So we're going to look for, we'll say at 24 hours, x is equal to 12. So we can just put 12 in our functions. So let's say f of 12 is equal to 8 times 1.44 to the power of 12. And that will give us our amount, 12. And that should give us our answer to question 19. So we have 8 times 1.44 to the power of 12. Is that right? Yeah, initial value base to the power of that. So we get 635.975. So we'll call it 636. Usually for values of discrete things like this, usually you round down, but that's going to be, we'll say about 636. We'll say about 636 bacteria. Put the exact value, 975 is approximately 636. Okay, this says approximately, so we'll say approximately 636 bacteria. So that's our answer. Number 19. Number 20, approximately how many days will elapse before there are 451,000 bacteria? Well, I'm going to do like I did in the prior video and go to the table view. I think we're going to be, hours might be a more appropriate thing. So we go here, and I'm going to get a Control I, add graph, and we're going to say 8 times 1.44 to the power of x, and we hit enter, and we've graphed that. We're going to be at 8 up here and continue up. We go to table view. Let me see, remember what that is. That's 451,000. So Control T. Okay, here we are. Now we said after 1 day. Okay, that's what that is, right? 636, right? And we're looking for 451,000. Here we are at 10,000 past 10,000. Okay, 64,000. Let me just go up here. Let's see. Seeing showing that. Wow, it's getting really high there. That's 743. Got to go back. Way too high. Okay, that's 5 million there. Okay, we got 934,738. Okay, let's go back. Okay, looks like between 30 and 31, okay, we're going to be there, and we're talking about 12 per day. So this is going to be during day 3. We go from x equals 30 to x equals 31. We go between 450,780 to 549, and we want 451, right? So that's going to be right around this 30, right? 451. So we'll say 30. We'll say x equals 30. So about 451,000 when x equals 30. And to find the number of hours, okay, hours equals 2x. So we have about 451,000 bacteria. When time equals 2 times 30 equals 60 hours from the beginning. So how many days will elapse? So this will be over 2 days. Now 2 days is 48 hours, so we'll say 48 hours plus 12. So we'll say about 2.5 days later. So that's assuming no constraints with food and all that. So that'll be our answer to problem 20. So again, example of real world use of exponential functions for modeling purposes. Good luck, and thanks for viewing. Before I go ahead and turn this baby off, I want to do one more thing. If about ready to torpedoes, problems 21 through 24 has this Beth running for exercise problem. So similar type of problem, exercise plan, exponential function. So now, good luck, and thanks for viewing.